My name is John Chandrasekhar, HOD Instrumentation, working with iFluids Engineering. Today we are going to discuss about how to prepare piping and instrumentation diagram, session 2. In first session, we have discussed about what is P&ID, how to prepare the P&ID, what are the sizes of the P&ID, and what are the symbols, basic symbols like equipment symbol, instrument symbol, and abbreviation we have discussed. Then we have discussed numbering of lines and tag numbering, instrument numbering, and P&ID arrangements like sheet continuation, unit continuation. Then we have studied about isolation type, single isolation and double isolation with drain, and winter protection, line heat tracing that we have discussed in the first session. Today we are going to discuss about specification of line braking, line class braking, and control wall arrangement, safety relief wall arrangement, basic process loop like feedback loop, feed forward loop, ratio controller, and cascade controller like that. Then types of tag blanketing and miscellaneous item and spec breaks. Specification break, which is defined as an area where high pressure piping transition to lower pressure rated section. Those are particularly vulnerable to ruptures or fissures and need to be monitored. For example, if you are having a high pressure line, the line after a vessel or after a compressor or after a exchanger, the pressure reduced, the process condition changed, no need to keep the same line sizing in the downstream also. It will cost your project cost. So you can change the line sizing. That is called spec break. Specification breaks or spec breaks are extremely important and it is not taught in college. They are noted on piping and instrument diagrams and indicate where a specification change has occurred on piping with regards to flange rating, metal rating, or insulation type also. We can change insulation also. They are very extremely important in hazardous and operability reviews when reviewing relief wall settings and the hazards introduced by creating overpressure situation by opening and closing walls downstream for a high pressure. So, line class break point. As a general rule, line class break shall be specified based on the following philosophy. There are 5 to 6 philosophies are there. One by one we will discuss. The line class break point shall be at the final wall if class break is required. We should include all the isolation wall and main control wall. The line break shall be at the downstream of the wall. Line class break point around control wall shall be at the bypass and block wall. If new line is connected to the existing line, class break point will be determined considering the design condition of the existing line. We have to take the existing line stream parameters only, not the new line parameters. Accordingly, we have to give the line breaking. High class due to the tube rupture of shell and tube type heat exchanger shall be applied to up to the upstream and downstream first walls of the heat exchanger. In a shell and tube heat exchanger, this line breaking shall be downstream of first wall of the heat exchanger. Okay, we will go to the next slide. Refer to the typical example. I am going to show a typical example below. Class breakpoint around pump shall be as follows. In a pump, it's a different type of pumps may be there, but the line breaking for the pump should be, there are 2 points. If pump discharge line class is 600 and smaller, pump discharge class shall be applied to the suction valve also when the spare pump is installed. If the pump discharge line is 900 and greater, pump suction line class should be decided by the upstream condition. It should not be same 900. You understand clearly. If the first line, if pump discharge line class is 600 and smaller, maybe it's 300 or 150, the upstream, the suction should be same. But in case of 900 and greater, it should be decided by the upstream condition, not with the downstream condition, because each pump have their own seal arrangement. The seal may be soft seals or Teflon seals or whatever, maybe the different types of seals. It may damage because of the 900 rating. That's the way we have to consider the upstream condition only. Same measure, safety relief valve should be provided for pump suction. In the case of higher discharge line, 900 and above, we should not put the same 900 in the suction line because there is some soft mechanical seals will be there. It will damage. That's the way we consider the upstream condition. Accordingly, we have to put the line glass. But we have to keep a safety relief valve in the pump section always because our section discharge line is higher rating. That's the way we need to put a safety relief in the section line. There are some licensed units are there. The licensor, they may mention what is the line break. So we have to follow the licensor units instruction. Project engineer will specify the breakpoint based on the applicable code. Sometimes international codes will tell where you have to break, what type of high grade and low grade you have to put, where you have to put. The international standards will tell. There are some typical example, control valve, you can see high grade and low grade. You have to see one thing, all the valves, isolation valves and drain valves inside high grade. Only the downstream only low grade. So we have to very specific, all the isolation valves should be in the high grade. Otherwise, if it is in the low grade, if high pressure gone, the valve seat may be damaged. That's the way we have to keep in our mind when we are doing the line class breakpoint. This is another type of line breaking for LPG services connected to low pressure. Here also this control valve, isolation valve, ball valve, everything inside the high pressure line. Similarly, safety relief valves also. Safety relief valve, main valve, that isolation valve, all are inside the high grade. Even this bypass line also inside the high grade. But in the discharge line is the low grade because it is going to atmosphere or some go to some flare gutter with a lower pressure. This is utility connection. In utility connection, there are two scenarios. One is the when process class is higher than utility class. Process line, the utility is going inside the process line. If process is higher, then that side is higher grade. The utility stream is lower grade. If utility class is higher, process is lower, then utility line should be higher grade. So you mention those things in your P&ID. This is another line junction. If there is one line, main stream line is going, you are going to put a junction. We have to keep this line breaking like that only. Low grade and high grade. So in this also you notice all the valves inside the high grade only. Okay. Then this is another low to high pressure and high to low pressure. These are the similar way, but we have to keep one NRV in this low to higher and high to low. We have to keep in low to high we keep one NRV. In high to low pressure we keep two NRVs, non-return valves, check valves. That's all. Now we are going to discuss about free drain and minimum. If you see the P&ID, somewhere else they mention minimum free draining and minimum. Wherever the draining is there, we have to mention the distance of the minimum distance. Otherwise, we don't know where it will be ended up. The draining or flushing or slug, we don't know. That's why we have to mention the distance. How much mm or inches or meters. The minimum drain we have to show in the P&ID. Now we are going to see how the control valve arrangement is inside the P&ID. Indication of instrument air failure action, failure to close or failure to open, we have to mention. Accordingly, the person who is reading the P&ID, he will understand how the stream is. For example, failure to close means some important hydrocarbons, no need to go outside. So that case, failure to close. But sometimes we have to drain the inventory, the hydrocarbon to drain drums or maybe the flare. So it is failure to open. When plant failure or ESD happen and instrument air failure or UPS power has gone, then this action will take place. So we have to mention F4, FC. Now we can see safety relief valve arrangement. Safety relief valve SV discharging into a flare shall be installed at an elevated location to provide discharge line with self-draining into the flat system. Suction line shall be free draining from SV to suction vessel or line. Typical arrangement of SV is shown below. In the SV safety relief valve, it is going to flap. There are two lines. One is the normal line, which goes through the safety valve. It has a CSO, CSO. What is CSO? CSO, car seal open. Means if the valve is open and put a seal. Always it is open condition only. Otherwise, somebody mistakenly closed, then there will be an accident. When pressure goes gone up, it will not go to a flare header. This SV will not pop up. That's why it should be CSO that we have to mention in the P&ID. If it is a bypass line, there should be one blind spectacle blind and two isolation walls. So that should be closed condition only. That should be always in the closed condition. When we are taking this SV for maintenance or something, that time it will be open. Now we are seeing the double valve arrangement, double safety valve arrangement. One valve is in the line, another is in the standby. When we are taking periodic maintenance of one PSV, the another PSV will be taken in the line. In this also, the right hand side is the CSO, it's always open. The left hand side is the CSC. You can see the mid line, that is the bypass line, always both are closed because it is have high pressure. That's the way both the lines should be closed, both the valves, LC, locked closed, both. Otherwise, there will be a chances of leakage from that valve. If one valve is open, so there is a chances of leakage. You can see the standby line, the down CSC is closed, down valve is closed, but the discharge valve is open because the down valve is subject to high pressure and the discharge valve is subject to low pressure. But when we are taking this standby SV on line, so once you open this down valve, immediately it should come in line. Otherwise, if it is taking time to open the discharge valve also, there is a possibility of discharge during that time. That's why one valve is closed, the upstream is closed, downstream is open. This is a safety valve arrangement. We have to mention accordingly in the our P&ID. There are some rules, some thumb rules are there. I am going to read this thumb rule of the safety valve arrangement. SV submeter may be provided when many SVs are required at a service location. In one service location, one process, there are many SVs are there, 2 or 3 more SVs are there, then we have to keep a sub header, that is dedicated header for these safety valves. You no need to put all the SVs in the vessel or some equipment. Better you keep a separate line for the SV. Then it shall be considered that SVs are located on the vapor outlet line rather than direct mounting on the vessel. If there is a vapor creation chances are there, then better you put this SV on the vapor outlet line instead of putting in the vessel itself. Outer vapor line shall be reviewed with the reference to AP RP 521 criteria. Block valves with CSO facilities and bypass valves shall be provided for all SV installed to protect pressure vessel and connected to flare header. Last slide we have discussed about the CSO facilities and bypass line facilities. 3/4 inches of bleed connection shall be provided on inlet and outlet line between the block valve and SV. Bleed connection is not required for thermal relief valves provided on the lines. Discharge piping to the atmosphere shall have 9 mm diameter weep hole at the low point and have no block valve on the discharge line. Actually, this weep hole, we have to consider this weep hole of 9 mm diameter in the discharge line because some of the discharge line going to flare or some of the discharge line going to atmosphere also. The line due to heavy rain or something, so there is a possibility of liquid accumulation in the line. Okay, it will affect the performance of the SV safety valves. That's why we have a small weep hole, so that liquid, the water which has condensated above the line will drain. Set pressure shall be indicated adjacent to SV. The set pressure of the PSV, SV should be noted in the P&ID addition to that symbol. If SV is located at high point of the full liquid surface, the set pressure shall be verified by taking account on the liquid head. For example, if you connected a SV in a liquid surface, in a top position, some elevated position, we have to calculate the header pressure also, that line head, what are the liquid inside, that pressure also we have to include while designing the SV. It will give some pressure. That liquid head also will give us some pressure. Okay. If the bypass line is used for vessel vent, its size shall be same as the vessel vent. Minimum bypass line is smaller of 1.5 inches or SV discharge line. Spare SV is not necessary to be installed on stream. If PSV SV is installed on a stream pipeline, there is no need of spare. Only one is enough. For the water cooler, SV is not required for cooling water line because CSO is specified for the outer wall on cooling water return line. So the cooling water return line is always open. We never shut off the cooling water return line. That's why there is no SV is not required. Okay. Now we are going to see safety relief valve arrangement. There are some 6 factors we have to consider when we are doing the arrangement. 6 factors that must be considered when selecting and sizing safety or pressure relief valves. Connection size and type. The valve size must correspond to the size of the inlet and discharging piping, and set pressure and temperature, back pressure, service and recovered capacity. The back pressure is very important when designing the PSV, because these PSVs are connected to a drain line, maybe or with a flare header. There are different types of PSVs connected to same header from different units. So that time, if any of the higher pressure PSV pops up, that pressure may come back to this PSV, which is in normal position, and damage the internal parts. That's why we have to think about during the design the back pressure of the line. That is very important. Now we are going to discuss about basic process loop, which are going to be mentioned in the P&ID. The first block is the one process in the line. Then there will be one sensing element, maybe pressure transmitter or temperature transmitter, RTD or flow RFS, like that only. Then there will be a measuring element and transmit element. Both combined are called transmitters. Then it will go to control element. Control element nothing but a DCS or single loop controller or dual controller or SCADA or maybe your PLC. Then it will go to final control element. Final control element is nothing but your control valve, shutdown valve, maybe some pumps or motors or compressors. This is the basic process loop we are going to study. Whatever I shown in the block diagram, it is shown as a fixation. This fluid line is here. On R phase is the flow sensor. Transmitter is there. One single loop controller is there. It will control the final control element. There are different types of process control loops. Feedback control, feed forward control, feed forward plus feedback control, ratio control, split range control, cascade control, and differential controls. Out of this, we are going to discuss some common type of control loops. First, we are going to see feedback control. One of the simpler process control schemes. A feedback loop measures a process variable and sends the measurement to a controller for a comparison to set point. If the process variable is not at set point, control action is taken to return the process variable to set point. The advantage of this control scheme is that it is simple using single transmitter. This control scheme does not take into consideration any of the other variables in the process. This is one small level controller. One LT is the level transmitter is there. So we are able to control the level. If it is more, this controller level control LC will take action. Then it is going to a positioner I2P and positioner. Then the LCB 100 it will close and it will control the inlet flow, so that there is no flow inside the vessel P100. This is the simplest control action. And this is the feed forward control. Feed forward loop is a control system that anticipates load disturbances and controls them before they can impact the process variable. For feed forward control to work, the user must have a mathematical understanding of how the manipulated variables will impact the process variable. In this example, we are going to control the heat, the temperature of the water. Maybe it is water. Water is coming inside the fluid in water or fluid, or some fluid is coming inside. There is one flow meter is there. Then we are sending steam to heat the fluid, maybe water or maybe some fluid. So our aim is to control the temperature after that one. Okay, but by measuring the temperature, we control the steam flow. The steam flow, how much fluid is going inside, accordingly the steam flow will be controlled. We are not giving excess steam inside this one. Normally this feed forward control is an anticipatory control. We call it anticipatory control. In PID algorithm, proportional integral and derivative will be used in this feed forward control, because in temperature we will not sense the immediate effect change of the temperature immediately. It will take time. If, for example, if the temperature is 90, if it goes to 95, it is taking little bit time. If you are taking a action immediately, then it reaches 95, then it will be a oscillation in the system. It will not be controlled. Then the controller will see the rate of change of heat increasing 95, 100, 105. So accordingly, some pattern, process variable pattern, it will see how the error is increasing. Then accordingly, it will take an action, anticipatory action. But this is have some mathematical understanding, means that P&ID algorithm. So that algorithm we have to understand. The feed forward control, an advantage of feed forward control is that error is prevented rather than corrected. Yes, before the error is going to happen, we are preventing, not feedback. Feedback is that once error happens, it is going to control. But in this case, it is going to prevent the error, not control the error. However, it is difficult to account for all possible load disturbances in a system through feed forward control. In a feed forward control, we can control only one disturbance, load disturbance, the major load disturbance. We cannot control other load disturbance. Maybe the previous example, we have seen this temperature disturbance, but not the flow, inlet flow, the fluid in and steam flow we are not controlling. We are measuring the major disturbance only. In general, feed forward system should be used in case where the controlled variable has the potential of being a major load disturbance on the process variable, ultimately being controlled. Next is the ratio controller. Ratio control is used to ensure that two or more flows are kept at the same ratio even if the flows are changing. Application: blending two or more flows to produce a mixture with a specific composition. Blending two or more flows to produce a mixture with specified physical properties. Maintaining correct air and fuel mixture in a combustion. In a boiler or combustion heaters, if air and fuel ratio, we have to keep some ratio, one ratio of fuel and two ratio of air, then this ratio control will be utilized. In here, one example, water and acid. 2 part of water, 1 part of acid is mixing in the tank. So there is a flow transmitter for water line, then another flow transmitter for acid. But this flow transmitter goes to FIC of the acid line. Similarly, this water line is going to FIC of the acid line. So according to the water, how much water is coming, accordingly this acid will be added. The water FT given a set point to FIC. Okay. Now we are going to cascade control. Cascade control uses the output of the primary controller to manipulate the set point of the secondary controller as if it were the final control element. Reason for cascade control: allow faster secondary controller to handle disturbances in the secondary loop. Allow secondary controller to handle non-linear valve and other final control elements problem. Allow operator to directly control secondary loop during certain modes of operation such as startup. Now in this case there is a shell and tube heat exchanger process is coming. We are measuring the temperature. This temperature controller giving a set point to flow controller, steam flow controller. So the flow is controlled by the temperature. The temperature controller is giving a set point to flow controller. This is the cascade controller. But during the startup, you can break the loop, you can remove the temperature controller, and you can use the flow controller as a single feedback controller. During the startup, we can use it. In this case, controller is very faster, and it is stable. Now we are going to see split range control. Split range control, very common control scheme in split range control in which the output of a controller is split into two or more control valves. For example, controller output 0, valve A is fully open and valve B fully closed. Controller output 25% open, valve A is 75 open and valve B 25% open. Controller output 50%, both the valves are 50% open. Controller output 75%, valve A is 25% and valve B 75% open. Controller output 100%, valve A is fully closed and valve B fully open. This can be reversed also. Instead of valve A, we can put valve B also. Both the cases we can take. So simply one transmitter, one controller, it is splitting into two. This type of control action most probably in the process gas outlet which is going to downstream process. Sometimes the process gas is higher pressure, some portion of the gas will be routed to flare or recycling. So that time there are two A and B two valves. One valve A is in the main gas line, B valve is in the flare line or recycling line or vent line. So according to your control output, this valve will open and another valve will be closed, and different scenario it will vent some of the gas so that the main process gas will be intact or our desired output. Now we are going to discuss about tank blanketing system by nitrogen. This is the general arrangement for a nitrogen blanketing in a tank. Any hydrocarbon which required nitrogen blanketing, this type minimum arrangement should be there. There should be two isolation valve, one spectacle plane, one non-return valve, one PCV pressure control valve. This is self-actuated pressure control valve. This pressure control valve, self-actuated control valve, getting a pressure from the tank itself. When the tank pressure goes up or down, based accordingly, this valve will open or close and allowing nitrogen inside the tank. There will be one pressure gauge. Then the valve lines, the downstream of the valve should be free draining. It should be a little bit slow so that the whatever the condensate in the line, it should go inside the tank. This is the general arrangement. Normally, this tank blanketing system in the top of the tank, located at the top of the tank. You have to mention in the PID accordingly. Now, there are some miscellaneous points which are to be mentioned in the PID. While we are making, we have to mention some miscellaneous points. The following specific notes shall be clearly specified in the PID. Startup line. Sometimes some lines used during the startup only. Normal operation, these lines will not be no use. During the startup only, this will be used. That startup line we have to mention. Then no packet. There is no packet in the line, steam line. There should be no packet so that the vapor trap or air trap should not be there. Then free draining. In the previous slide we have shown the free draining. It should have a small slope so that the whatever the condensate, the liquid should be drained freely. Then gravity flow. Sometimes the flow through the gravity, it will happen with the gravity. Then we have to mention it is gravity flow. Then slope. We have to show the slope. How much? 1 is to 10, 1 is to 100, 1 is to 1000. That small triangle we have to mention above the line and we have to mention the slope. Then minimum maximum length requirement. The first slide we have seen the minimum drain requirement. What are the minimum length requirement? Then symmetrical piping arrangement. Symmetrical piping arrangements mean there are two pumps A and B, two compressors or three compressors A, B, C. The piping arrangement should be symmetrical, same elevation, same length. The suction getter as well as a discharge getter. It should not be a different piping arrangement. Then typical vent and drain size of piping shall be 3/4 unless otherwise specified. Normally, default the vent and drain size of the piping shall be 3/4 inch. Otherwise, specifically if the licensor mentions something, then we have to change them. When a wall is CS and its size is 1.5 inch or less, welding connection should be applied. When small bore lines 1.5 inch or less CS line, the welding connection should be applied. There should not be no flange connection. While the flange connection is applied for 2 inch and above, other sizes 2 and above, we have to use the flange connection. For alloy walls whose rating is equal to or greater than 900, typical connection shall be by flange regardless of its size. If it is alloy walls and if it is a 900 rating, whatever may be the size, it should be flange size only, flange connection only. You should not go for a welding connection. For 1500 and greater, all of walls, including control walls, will be butt welded, regardless of size, material, or wall type. If you are going to select a higher rating wall, the wall should be butt welded, regardless of size, material, or wall type. Minimum shall be indicated in the P&ID for the following points to minimize the pipe dead end between isolation wall. Two isolation walls are there, the minimum, what are the minimum distance? The connection point of purge out. If you are purging something and purging is going out, then what is the minimum distance? Otherwise the line will go somewhere else very long distance. So it is not desired. Then connection point of slope out. For the lines in which two-phase fluid flows and vapor packet is not avoidable, show two-phase flow on P&ID to provide against vibration problem and flow measurement. There are two-phase fluids flow in a stream in a line. Their vapor is not avoidable. Then you have to show two-phase flow. That note you have to put in the line. V pole shall be provided at the low points in discharge line of safety relief valve, rupture disc and silencer discharging to atmosphere. The hole diameter is 9 mm and indicate 9 mm WH. Already we discussed the V pole in the safety valve arrangement. So wherever safety valve and rupture disc and silencer is there, because it is going to atmosphere, there is a possibility of rainwater or some condensate inside the pipeline. It will create the corrosion or damage the internal parts of the walls. That's a V pole is important. We have to mention minimum 9 mm WH. Then this is the revision history and hold. If some package item is not available during your preparation of the P&ID, you have to put hold or you have to put a one box and pack so that the customer client understand this is a second revision, it was updated. Otherwise, he has to go through the P&ID again once again. It will take time. In the second session, we have studied about specification of line class break, control of arrangement, safety relief of arrangement, basic process loops, type of process control loops, dam blanketing, miscellaneous items, and revision history. That's all. All the best. Thank you.